So we'll first start with the first topic, which is the introduction. So here we'll kind of look at what are all the components which are there in an embedded system. We'll understand what it means to be an embedded system. Then typical characteristics of an embedded system. Like when you say characteristics, what are the features which are unique to embedded systems? And we'll contrast it with general purpose computers, because all of you are familiar with general purpose computers. You keep using laptops or PCs or whatever, so you're familiar with what it is. So taking that as a basic example, how an embedded system is different and what are the areas which are common, what are the overlaps which are there, and how you say whether it's an embedded system in a true sense or not. And we'll look at some example embedded systems, and then we'll also a little bit more focus on embedded systems as a whole class. We'll look at what do you mean by real time. There are different classes of real time systems, and there's a huge variety today, especially in the modern world today. We have a huge variety of things which you can call embedded systems that are overlaps. So we'll look at some of those examples as we go along actually. So that's going to be the broad agenda for this first session. And let's move on to what you understand by the term embedded system, right? The most, I think when we say embedded, the most important thing which distinguishes it from many other systems is that it's generally built for a specific use case. I mean, most embedded systems, we'll talk about some things which kind of probably blur the lines. Probably you can look at mobile phone. You can call it as an embedded system, but you can also look at it like a general purpose computer, right? There are things which are, because of the advancement, in the VLSI, the power that is available in a small form factor device, a lot of things are possible. But a classical embedded system typically is something which is built for a specific use case, right? You take this example, this projector. It's actually an example of an embedded system, right? It has its own processor, it has its own good amount of software. Some of them even run Windows nowadays, but traditionally it'll have a small embedded software which controls the projector, the lens, the keypad which is there. So it's a purpose-built device, right? Which is an example of an embedded system. The air conditioner, for example, right? Today, modern air conditioners, you have a remote, you're able to control it, which means, on the other side, the remote itself we can say is an embedded system because it's a small microcontroller which is able to transmit maybe over IR or Bluetooth or whatever. Similarly, on the air conditioner itself, you'll have a small microcontroller which kind of receives the signal. It is able to operate the motor, the thermostat controls, and all that stuff, right? So these are all classic examples of embedded systems, and today, we have them all around us. If you look at this room alone, you can count so many things which are embedded systems, right? You have smart lights, smart bulbs, smart controllers. There are so many things which are all embedded systems. We don't even realize today because there's so much microcontrollers embedded in a lot of everyday devices. We often don't think about it as an embedded system. This remote for this that you use to control, it's actually a small embedded system, right? So the most important thing about an embedded system is generally it's built for a specific use and a specific use case. So it's kind of custom built. And if you look at maybe 20, 25, 30 years back, right, many of these were probably completely built with hardware. I mean, they may not have any software itself, right? It could have been a completely digital logic. Some of your VLSI, right? You could have actually implemented everything in custom digital logic. Maybe use a PAL or something if needed. But the entire thing could have been built completely in hardware, which might have some sensors and basic things to operate, right? Even today, there are probably some devices which are completely built in hardware. But increasingly, because of the advancement in electronics and VLSI, microcontrollers have become pretty cost efficient. They're much cheaper than what it used to be 30 years back. So today, for convenience, and the moment you have a microcontroller and you have a software, you get a lot of flexibility and ability to upgrade the device without too many hardware changes. So most modern embedded systems today are typically microcontroller or microprocessor based. But if you look at 20, 30 years back, it was not necessarily the case. It could have been a completely custom built hardware for a specific function, right? So, and again, today, because of the advancement in the processor technology and all that, right, you have a huge class of embedded systems, right? I just taken some examples here, like for example, a water level detector. It's an example of a very, very simple embedded system, right? You just need probably a couple of sensors, maybe one to sense the high water mark, maybe and so on, and one for the low water mark probably. And all you need is something to turn on and turn off the motor. I mean, it could have been actually built if you're VLSI background or if you're done electronics. It's easy to imagine how you can do it with just hardware, right? It's probably quite easy with a few sensors and some switches to control some relays. You could have probably done a simple circuit which is just monitoring two sensors and taking action to either turn on the motor or turn off the motor. It's a very simple embedded system. But today, that can be built with a small microcontroller. The sensors will be inputs to the microcontroller, and there's a small software which keeps monitoring the sensor parameters and keeps polling it or whatever, right? Keeps checking the sensor inputs and then takes a decision based on that. And that gives you flexibility. You can actually enhance it. You can add functionality. The moment it is software, you'll probably be able to modify that whole logic as you want. You can take decisions. Should I fill the tank all the time? I can add one more sensor. If I'm pumping from a underground sump, I can probably add one more sensor to check whether there's water there. So the moment you bring in software and microcontrollers, the biggest advantage we get is flexibility. And you can change things as you need, and you can actually have a basic design which you can actually improvise upon as you go along, right? So that's a very, very simple embedded system. Maybe if you look at the extreme other end of a very, very complex embedded system, right? Today you're looking at autonomous driving vehicles, right? Today the famous one is Tesla in the US, who are actually trying out autonomous driving, and there are autonomous taxis in the US, right? You can order a taxi, the taxi comes to your doorstep, you just get in, tell where to go, it drives you and drops you there, right? Today, those things are a reality, at least in the US, where the traffic is probably a little more disciplined and controlled and all that. But if you look at that system, you can say it's an embedded system. Its whole purpose is to autonomous driving vehicle, right? That's a core functionality of that. but it is pretty complex because it has all kinds of sensors, radar, lidar, it senses GPS, proximity sensors, image, it processes a lot of images also. It senses the velocity, basically the speed and the direction which the vehicle is moving. I'm sure there are many more sensors in a typical autonomous car, right? And it has to process all of that in pretty much real time, right? If you are driving a car at say 60 miles per hour, the speed at which you need to process the images, the radar, it's also pretty real, very real time response is needed, right? You see a pedestrian crossing the road, you need to apply the brakes in time to stop the vehicle. So it's an example of a very high-end embedded system. It's custom built. They use probably, I don't know how many processors are used today. They use GPUs for a lot of processing. So a high-end autonomous vehicle, which is say, safe to be operated, right? It's a very complex embedded system. It synthesizes all these sensors, inputs, and has to take decision quickly. They in fact now have probably even artificial intelligence-based decision making. A lot of things are going into that, and that really is a good example of a very high-end embedded system. It has a lot of time constraints. It has to act immediately. You cannot delay the decision, right? I see a image change, somebody walking or a car cutting in front of me, that has to be processed in probably microseconds to take action, apply the brakes, or take something to avoid a collision or whatever. So today those things are becoming, this is a complete autonomous car, but there are, even in India today, you have devices like many cars are equipped with what they call ADAS, right? ADAS level 1, level 2. These are all driving assistant. They're not complete autonomous, but they provide you indications in terms of whether the lane ahead is clear or you following the lane. The senses vehicles coming on the side. Modern high-end cars today in India also are available. And these are all examples of embedded systems which senses different levels of input. They are not completely autonomous, but they do provide you information in terms of what's really going on around the scene, so that you can take action proper. As a driver, you are provided the information in time to take actions actually. Okay. So that's an example of a high-end embedded system. So the important thing to remember is an embedded system is something which is purpose-built, which is actually custom built for a particular functionality. Functionality will be very simple. The trivial one that we saw, like a water level controller, a detector, or whatever, could be as high-end as an autonomous car, right? And there's a huge spectrum of devices in between. So that's the key thing that to remember about an embedded system, right? Now let's move on to see a typical, just a very high-level abstract view. We're able to see the screen where you see us. This is an example of a microprocessor-based embedded system. We'll be more and more spending time on that. We are not going to look at pure hardware because that's pretty much not very common unless for a very trivial application. Most embedded systems today are microcontroller-based or microprocessor-based. And what you can see here is a typical diagram. As you can see, the heart of the system is a CPU, which could be a microcontroller or a microprocessor. And if it's a microcontroller, you see the memory, the read-only memory, the random access, the RAM, the ROM. Those are all typically on chip. If you take a typical microcontroller, it has a small amount of read-only memory, RAM, or a flash type of memory. It's all built onto the chip itself. And you'll typically have some input and output devices which are connected to the pins of the microcontroller or the microprocessor. You typically will have some communication interfaces to communicate with the external world. And there could be additional application specific, like maybe a specific functionality. You may have additional ICs or some circuitry which does certain things. Typically, you will have things like sensors or A to D converters, many other things which are possible. If you have a high-end microcontroller, a lot of these are built onto the chip itself. So if you look at this diagram, where the chip boundary is flexible. Like for example, the chip may contain the CPU, the read-only memory, the random access memory, some of the input-output, all could be part of the microcontroller itself. Or if you're using a general-purpose microprocessor, some of these may be built externally. The RAM and ROM could be external devices which are interfaced through the typical bus that the microprocessor provides. So it can be either way, but typically any embedded system, microcontroller or microprocessor-based embedded system, you can actually abstract it to this view. It's helpful to understand this because when you look at any system, you can mentally understand where the boundaries are, what is doing what, how do I partition the system, is it on chip or off chip. So having this model helps you to understand an embedded system pretty easily. So this is just an abstract view of an embedded system. Most of them will conform. There could be some variation, but this is a good thing to have in your mind so that you kind of appreciate when you look at a new system, an architecture or a block diagram, you'll be able to kind of understand it from this perspective. Then it becomes easier for you to get into the details of the embedded system and go on actually. Okay, so let's little bit more about what are the other attributes. So the first thing we already talked about, right? The most important thing is it's typically single function or single application. That's the primary attribute of an embedded system. We already talked about it. And in general, right, an embedded system is generally a closed system. You will not allow the users to run additional things. Though it's a microcontroller based system or a microprocessor based system, generally the user will not have ability to load whatever he wants, right? It is typically a closed system in many cases. There will be user interfaces through which the user can interact with the system, but you cannot arbitrarily write some program and upload. Generally, it will be locked or prevented in some fashion so that you don't mess with the system. The reason that is done is typically embedded systems are built with a very tight integration of hardware and software. When I say tight integration, it typically means the hardware, the capacity, the the horsepower, or in terms of MIPS, right? What is the processing capacity needed is generally kept to the required level, because it ultimately comes down to cost, right? So if you look at typical microcontrollers, right? If you want to buy a microcontroller which can run at say 50 megahertz, it probably will cost you probably few cents or something, or maybe $1 or so. But if you want to run a processor at say 500 megahertz or 1 gigahertz, right? It's going to be a costly chip, right? Again, the process in which it is made or whatever, everything affects the cost finally. So that's one of the reasons why if I am an embedded designer, I'll make a very tight integration. I'll choose the hardware, I'll choose the software, the amount of memory required, the software footprint, everything is tightly controlled by the designer. So I will not add unnecessary cost to the system by keeping a large RAM for users to run things, right? If I know my entire software can fit into 16 kilobytes, that's all I'll put. I'll just choose the lowest cost device available, keep the memory footprint to the minimum. And that's one of the primary reasons, both in terms of memory, in terms of the CPU MIPS available. Embedded systems are very tightly built. And that's the primary reason why you don't allow the user to arbitrarily run things on that. Though you can say it's a microprocessor, why don't you allow the user to run something on that? It doesn't make sense, because the system is built for a purpose. It's built very, very tight integration of the hardware, software, the memory footprint, the hardware, the CPU capacity, the peripherals available, everything is tightly controlled. So that's the primary reason why you don't allow the users to arbitrarily load things and run things. So it's all custom built. Everything is kept to the minimum or the adequate amount required so that the functionality is met, but we are not wasting money by investing on a large chip or a large capacity CPU unnecessarily. Okay, that's one of the primary things. And most embedded systems will have constraints in terms of time. Time, when I say time, typically embedded systems, as we saw, right, has some inputs and outputs. They have to react to some events. They have to take action quickly. We saw the example, even if it's a water level controller, if the water level the tank is empty, you expect the device to immediately start the motor, right? You don't want to wait for 5 minutes to start the motor. Then, somebody opens the tap, they're going to find that there's no water, right? So you want to prevent events like that, or a user dissatisfaction. So embedded systems typically are built to respond timely to events that happen. Take an example of that autonomous car, right? You would act immediately. It's a lot more real time. Maybe the motor can take 1 second, maybe it doesn't affect, or even 10 seconds, probably it's fine. But whereas if it's an autonomous car, or there are other examples which we can look at later, you need to act much, much more quickly, probably milliseconds or microseconds, depends on the class of systems that you're dealing with. So any embedded system will have to support tight constraints on time. That's a very, very important aspect of embedded systems. We'll look at some things which allow, we'll talk about it later in the course, how an external event can, get attention immediately and so on. But that's another important feature of an embedded system, where you have to act immediately, right? Take the remote and press a button. You want the thing to turn off immediately, right? If it takes 2 seconds, you feel something is not working, right? I mean, sometimes it happens at home, you take your remote and switch on the TV, sometimes the battery is low, the signal doesn't go, you feel something is not working, right? So every class of system has an expected response time. Maybe human, like for me to register that something is turning on, maybe in a second or a sub-second response is good enough, maybe half a second is good enough. But if it's something which controls a car or whatever, you talk about milliseconds, microseconds and so on, right? So each system has a different expectation, but most embedded systems will have some expectation of timely response to events. Actually, that's another very, very important feature. And if you look at embedded systems which are battery powered, for example, this remote, right, which is a battery powered device, you have to also be worried about conserving power. You don't want the battery to run off very quickly, right? I put 2 AA batteries, I would expect it to last at least a few months. I don't want it to kind of go bad quickly or whatever. So that's another important feature. Today many embedded systems are battery powered. So you really want to design the system in such a way that it is conscious about power usage. Today modern, I mean, some of you, if you have done the VLSI, you would have seen how chips are today built with support for power savings. There's a power management module on the chip. You can turn off devices which are not needed, right? I mean, most of the time the CPU will be in a sleep state. I can turn off power for maybe most of the peripherals, only one input which I need to sense. Maybe somebody presses a key. That's probably the only thing that I'll be sensing. So today the devices also support, the hardware is also supporting a lot of power management features. So the software also has to be written in such a way that you make use of all the features and you ensure that you are not actually wasting battery power, which is precious. Devices take different strategies. You may have devices which are probably deployed remotely, right? You take example of things like wireless sensor devices, right? They are kept in remote places. Maybe they are kept under a bridge to sense the vibration of the bridge. and you can't service it so easily. Servicing it is costly. Device itself may not cost much, but if I had to send a technician to go change the battery, that may cost me, quite a bit of money. So typically those devices will employ methods to conserve power. They will probably turn off, sleep for a long time, wake up, sense, and then go back to sleep. So these things are all important when you design an embedded system. Most embedded systems today, they work on battery power. So you need to kind of worry about how I conserve the power. Even if it's grid power today, there's a lot of movement towards, conserving energy and all that, right? So today, in general, it's a good idea to conserve power. So the embedded system designers also have to think about what are the constraints that I have and conserve power. Again, all of these are related, right? Today, if you are, some of you, since you are in VLSI, you have actually ways to conserve power, right? There are many silicon, CPUs, they allow you to switch to a lower frequency and save power, right? You want to boost, you want to do some expensive computation or computation which is very fast, you can actually switch the frequency to higher compute, then go back, right? Most modern silicon SoCs provide you to change the operating frequency that you want and conserve power when it is not needed, right? So there are a lot of ways to do it. So as an embedded system designer, you have to be aware of all that, right? I mean, if you're a general purpose software designer, you generally don't worry about those things. But if you're an embedded designer, you have to worry about what features are available in the hardware and how do I kind of link them together so that I can make the best use of all the hardware support to conserve power. So just example that I talked about, voltage scaling or frequency scaling. A lot of things are available to conserve power on a typical modern SoC. So you use all of that and you kind of try to conserve power. So that's again another important feature of an embedded system. So these are the typical attributes. There could be a few more, but I'm just highlighting what is the most important things here. And some other things that you have to worry about when you design the system, right? I mean, we talked about cost briefly when I talked about why it is tightly put together. That's an important aspect from the hardware angle. There's also a software cost, right? Many of the times, if you have to use a commercial real-time OS like say a VxWorks or QNX, very industry standard operating systems or real-time operating systems for embedded systems, you have to pay a license fee. For every device I ship, right, I need to probably pay a few cents or $1 depending on the system that you have. You have to pay license fees to the software vendor also. So cost is not just in the hardware, there is a cost even in the software side. And again, the complexity of the system will determine what you need to use, right? I mean, if I have to build a system which requires a real-time operating system, maybe there is no choice, I may have to go it. And there, again, there could be choices. Maybe a low-end real-time OS where the royalty costs are probably not very high, whereas a high-end one may charge a lot more. Depending on the system, you have to make a trade-off. So cost is something that you keep in mind. Hardware we talked about in terms of choosing the right microcontroller with the right level of capacity in terms of on-chip RAM, ROM, or the processor frequency at which it runs. All the other devices on the board as well, not just the microcontroller. Any of the other devices that you choose also, you'll always be conscious of the cost. Then the next parameter, which is reliability, right? And this you can say is probably orthogonal to the cost. Like if you want to build a system which is reliable, you always want to have some better margins, right? You may want to choose a silicon which is having a better grade of reliability. It again depends on the operating environment, right? If I want to send, say, an embedded system to space, right? You need to build what is called as radiation hardened systems. Like, in the outer space, you have a lot of solar radiation, things which can actually affect typical silicon that we use probably on Earth. Here we are shielded by the Earth's magnetosphere, so you don't really get a lot of the problems that you are in outer space. Once you go beyond the Earth's atmosphere, you may get radiation related issues and so on. So you will build devices with a different class of hardware. Or if your system has to work probably close to say a boiler, you are having say a pressure sensor which is operating in a boiler, right, which is a very critical device. The boiler operating temperature may be much higher, even if you put all the shielding, insulation and all that, but you may still need to operate at a much higher temperature range. Maybe most silicon, the temperature range may be, the ambient temperature, they'll say 45 degrees or 50 degrees, right? On-chip temperature may be much higher, but the ambient temperature which is needed for the device to cool, maybe 45 or 50 degrees or whatever. But if you have to operate in much harsher environments, or you are putting say a embedded controller on an automobile which is close to the engine, right? Again, the temperature that you may experience there, the ambient temperature may be much higher. So again, you have to choose the devices based on, the operating environment. So that again may add to the cost, but it's a trade-off, right? As your embedded system designer, you'll have to decide, I need reliability also, right? I can't build only for cost and the device will, fail within the first week. It doesn't help me, right? So you need to kind of balance between cost and reliability based on the application. Maybe a device like this, like a remote control for this, probably you don't have to worry so much about it. It's mostly in an air-conditioned environment, ambient temperature is fine, so you don't worry about too much about it. So it depends on the type of device that you are building, and that will decide, what's the reliability. Again, reliability is also in terms of the software, right? If I want to really build something, an equipment for say a nuclear reactor control, so that software has to be extremely reliable. And that means one is, when I design itself, I'll follow a lot more guidelines in terms of software design. What are the things to be taken care when I design a system like that? There are a lot of good principles for reliable system design. And then I may do a lot more verification. I'll also spend a lot more testing, maybe 100% coverage testing for the software. All that will also add to the cost, right? Design cost itself goes up. Maybe it's not a production cost, but it's a design cost. typically the software development effort is a one-time effort, but based on the amount of effort you are putting in, the design cost will go up. Hardware typically is also a running cost. I mean, the hardware, you choose a costly device, every device you build is costlier. So both you need to trade off in terms of what you want to do. Then the next important aspect is upgradability, right? That's actually most modern systems, it's almost an understood feature. If I have any device today, I pretty much expect that to be upgradable on the field. You call it over the air upgrade or field upgradable. So if I have you have a router at home, right? All of you probably have a home router. Most of the devices upgrade themselves, right? Because they're connected to the net. They keep checking for, firmware upgrades available. And you click a button, they will prompt you saying, can I upgrade? Your modern smart televisions, right? Often my smart TV at home prompts me saying, when it turns on says upgrade available, should I upgrade? So you click a button, that's automatically the software which is there on the TV downloads the image. It takes a few minutes, it upgrades itself, right? Today, most embedded systems, there is an expectation that, it is upgradable. More complex embedded systems, they may even support an hardware upgrade, right? You may have a little more complex embedded system which has, say, multiple hardware cards, right? Some of them will allow you to upgrade a card or a chip at a time. So if there's a new modern CPU available with the same pinout and it's on a socket, you may be able to remove it and put a new one. And some of them even support probably, hot pluggability. I mean, very high-end embedded systems you cannot stop for any reason, right? They will support hot pluggability. You will be able to plug out a module. They'll be redundant systems. I mean, I'm talking about really high-end embedded systems which are, built for very, very mission-critical applications where you cannot even shut down the system anytime. So it will support hot pluggability. You can pull out a card and put in a replacement card. So there are a lot of different things that are available. Software upgradability is most common, but you may also even have hardware upgradability in redundant systems which are possible today. And the other thing is, serviceability, right? Can the system be serviced easily? Can I do a component level replacement if something fails? Or, is the repair even possible or not? So again, depending on the class of systems, some things will be expected. If it's a low-cost device, nobody is bothered. You throw and then get a new one. But if you're talking about a high-end system, serviceability and all becomes important. How much can you service the device without causing a lot of downtime or whatever? Those things become important. Right? I mean, maybe a field engineer can visit, quickly change and reboot and go. But if it's going to take 2 days, that may not be acceptable. So it again, all these depends on the class of device that you're talking about. But that's another parameter that you have to think about when you design the hardware, when you design the software. What is serviceable, what is not serviceable, right? So these are some of the design parameters that you have to keep in mind as an embedded system designer when you actually are building the device actually, okay? There could be a few more. These I'm talking about the most common ones actually, right? Now, we talked a little bit about, what a typical embedded system. Now it's kind of easy to contrast it with, what a general purpose computer that we are all familiar with, right? All of you are having a laptop in front of you, right? It has its own operating system. And one of the most common things that we do in a general purpose computer system is we run multiple things at the same time, right? All of you, I'm sure, have at least 10 applications open. You have a browser, you have Word, you have Google Meet running. All of them are running at the same time. And when I say at the same time, I mean modern laptops, of course, have multiple CPUs also. They're all multi-core devices. But at any point of time, a single core may be kind of doing multi-programming between multiple programs. You get an illusion that all of it is running at the same time, but they time share the CPU, and you kind of know that all things are making progress at the same time. But at any point of time on a single CPU, maybe one program is running. It may run for a few milliseconds, stop, then another program will run. But at a higher level as a user, you perceive that all programs are running concurrently at the same time. Even if it's a single CPU system, you still feel that all are running at the same time, right? So, and in a general purpose system, typically you don't have too many very tight timing constraints, right? You click something, it takes a few seconds to open, you understand, okay, it's opening, you're not worried, right? Only if it gets really bad, you open 100 browser windows and keep, you will see the system starts really slowing down, which gets irritating to a user because you are probably running out of memory. So the operating system is actually moving programs from disk to memory and so on. That's called swapping or thrashing. Then you start noticing a degrade. But there's a lot of leeway. You can probably open 20 programs without actually getting impacted, without really worrying about what it is. So you start getting bothered only when the system is pushed to the extreme limits. So that's general purpose systems. You generally have very little to worry about constraints. And when you write a program, you are not, and especially in the modern world when the CPUs are running at 2 or 3 gigahertz or whatever, a lot of memory. People who develop programs for general purpose computer systems are not so worried today. Maybe like 30 years back when the first PC had say 640 KB of memory or whatever, right? Things were a little tight. People are worried about optimizing and all that. But as systems have grown, the VLSI has improved, memory costs have fallen. Today, most laptops have at least 8 GB of memory, and it's quite common to have 16 GB memory. You have 1 terabyte or more of hard disk, SSD drive. So you're not, today, people who develop applications for a general purpose computer, software designers, probably you can say are got spoiled because they're not worried so much about optimizing the last bit of memory out there. They kind of use languages which give you a lot more comfort. You develop in Java or something like Java itself has its own system. It uses its own memory. It has its own virtual machine. But you're not worried about it because the designers are comfortable with the features that are available. So in a general purpose computer system, that software designers have very little to worry about in terms of memory or CPU capacity. They kind of don't worry too much about it. They more worry about the functionality, the user interface, make it look beautiful. They spend a lot of CPU to probably render things very nicely and all that, right? So typically on a general purpose system, the constraints are in terms of time or even the CPU bandwidth, memory, everything is lot less. So that designers, the software designers, can actually take lot of leeway. They can design with a lot more freedom, and they're not worried about it, right? I mean, even if I'm writing an algorithm, I'm doing a numerical computation, I can optimize it and make it run in 1 second. But the user is okay to wait 4-5 seconds. I'm not going to put too much effort, right? Because that's not a huge difference for the user. I type a command, 3-4 seconds, I get the result, it's fine. Maybe if I optimize it really well, it may complete in 1 second. But generally, you don't spend too much time doing that because of the abundance of hardware resources, the speed at which the CPUs are running today. So people have got used to that. Whereas in an embedded system, that's not the case, because as I talked about, right, embedded systems, you're still worried about cost, you're still worried about performance. More importantly, you're worried about the timing constraints, right? You are really have to respond to time. Let's just take an example of something. Say you are having a rocket control system, right? You launched a rocket, right? The rocket, you know what speed it goes, right? If you had to escape the Earth's gravity, you have to travel at a significantly higher speed, right? And you have to control the rocket. Some of you might have seen the launches in ISR or whatever, right? They really do a fantastic job of showing that path, right? I mean, you must have seen the projected path and the path the rocket takes. It's really, they closely track it, which means the amount of timing, control and precision that they have built in, right? So suppose the rocket launches vertically, right? Typically, rockets don't keep going vertically. At some point, they are a turn. Maybe at when they reach a altitude of precisely say 4 kilometers, I may have to tilt something in the rocket. Maybe some called control surface, right? There'll be some fins and all that, right? You may have to move that to change the aerodynamic pressure on the rocket to tilt. So that control has to happen precisely. Maybe when the rocket reaches say 1 kilometer altitude or 2 kilometers altitude or whatever the case may be, right? But you imagine the rocket by the time would have already be going at maybe a significant speed. Maybe it has already hit say 4 kilometers per second or 5 kilometers per second or whatever, right? Which means you hardly have, and you have to predict when it will reach that. You have to have everything ready. The control systems have to be activated. So the amount of the sensors may be giving you input. You may have an altitude sensor giving you input. By the time the altitude says say 2.5 kilometers, you have to get everything ready so that, and you should also be calculating that, okay, next probably 100 milliseconds I may reach this, and at that time I have to activate it. So all that has to be precisely calculated, and your embedded system has to be designed, the CPU capacity needed, the time it takes for the sensor to give you the input, all that has to be calculated precisely, and only then the rocket launch is going to be successful, right? So even if you are say 10 milliseconds late, the rocket trajectory may be very different. It may, instead of landing up in a particular orbit, it probably may not even reach the orbit, or it may go overshoot it or whatever, right? So embedded systems typically are very many embedded systems, high-end embedded systems have very tight controls. You have to be able to sense, predict. You may have to do a lot of simulations, right? Because if I talk about this system, you don't know in real world what will happen. So you'll have to have a lot of simulations to factor in a lot of things when the input comes, how much time I really have. This is the process I'm going to do, run it and see how long the computation really takes, right? This loop to calculate the trajectory, how long it is going to take. So essentially, these are things which really are, the distinguishing factors, right? If an embedded designer, you have to work closely with your hardware team, the software team. When the sensor, what is the latency of the sensor, how quickly I need to keep checking it. So there so many things go into actually designing a high-end embedded system. Whereas in a general purpose system, the software designer is generally a lot more free to take his decisions, not too many constraints. That's very important distinction. The timing constraints is very important. As I said, very little worry about the memory footprint or the CPU bandwidth available, right? And generally, when the embedded designer, right, you have to also have a good view of all the hardware resources. Like, if I'm writing a program for a general purpose computer system, a lot of things are abstracted out for me. I mean, I have an abstraction of a file system communication. I don't worry beyond that. I don't even worry about what is the hardware on my system, right? If I'm writing program in Java, the Java program runs anywhere. So I can write it on a Windows machine, it will run on a Linux machine, right? I'm completely abstracted out of the hardware, underlying hardware or whatever. And it's like really, I don't have too many constraints. I may run that program on a system which is lightly loaded or heavily loaded. Still it will run. It may just take a little longer or more, right? But the program will still run. It's not going to fail because I ran that Java program on a highly loaded system. Whereas an embedded designer has to really be clear about all the things in the system, right? I need to know what are the hardware peripherals, what is the timing for each one of them, how frequently I have to check all the inputs. If there are say 20 sensors, how quickly I need to keep checking them so that I don't miss an event. So the embedded programmer, embedded software designer has to have a very good understanding of the underlying hardware. You should know what resources are available, what timers I'm having, what are the sensors I'm having, how many interrupts I'm having. So they have to really understand the hardware very clearly, and they have to probably plan out things in very proper sequence. They should know if I'm choosing a 100 megahertz CPU, this is the time I'm going to take to run this loop. So a lot of hard work goes into planning the system, and putting it together. And as I said, it's tightly built, right? So I really have to plan the sequence in which I do the actions in all scenarios, all conditions, and that is the reason you generally don't add other things. Once I have built it, it's frozen. I mean, the hardware software design is tightly coupled and frozen. If I had to make something a change, I'll have to redo a lot of things. Because if I'm going to say, for example, somebody comes and says, I want to add another sensor to this device. It's not an easy job in an embedded system, right? Because addition of a sensor may mean writing some more software to check that. That new sensor may need checking probably a lot more frequently than what I have designed today, which means I need to look at, is there enough bandwidth on the CPU to do that? Can I really add that sensor without changing the CPU frequency or the grade of the CPU that I'm using? So all these comes into play. So that's where, any change to an embedded system, it's not easy. If I had to add a program or add a functionality, it takes a lot of effort, especially a tightly built embedded system, which is a lot of real-time constraints. You have to spend a lot of time looking at all the features of your system and really decide, can I add it or not? So that's another important thing. Like, if I want to add a sensor also, it's not easy. It takes a lot of effort from the designers. The hardware and software team have to sit together, discuss, decide what's the best way to implement it actually, okay? And but whereas on a general purpose system, you don't even ask, right? So somebody gave you this laptop, Bill Gates is not, or whoever is running Microsoft is not worried what you're running. So it's a general purpose system. You run arbitrarily whatever you want, and at best, it becomes slow. Then okay, this is the capacity of my PC. I can't run anything more. But you don't have to worry about running any new program on a general purpose system. Not just laptop. Even if you take larger computers, mainframes, or large servers and so on, right? People run all kinds of things, right? Today, if you look at the cloud-based systems, so you have a server, a hardware which is virtualized and shared maybe with 20 different clients, and they all run whatever they want on that, right? As long as they get the adequate performance, they are happy, and the underlying hardware multiplexes everything so cleanly, which you don't even realize what's happening. So the issue for a general purpose system is, very, very minimal. Designers don't have to worry about too many things. You can arbitrarily run. As a user, you have all the freedom to, run whatever you want on the general purpose system, okay? Now let's look at a few, we already talked about quite a few, in the previous few minutes, but this slide gives you a little more example of, different classes of embedded systems, right? For example, let's start with the simpler ones. On the right-hand side, we talk domestic appliances, right? We saw a few things, remote control for your TV. The TV itself today is an embedded system, right? All smart TVs, you can say, are embedded systems. Even the older ones had a small embedded controller for several things, but modern TVs, smart TVs are, pretty much good examples of embedded systems. Your air conditioners on your house, your washing machine, right? Your washing machine has an embedded microcontroller in it, right? You have a touch panel where you can program things. It has a lot of sensors. It senses the water level. It senses the load. You must have seen, right? When you start the washing machine, right? It does a few movements to check, what is the really load, right? It probably has some current sensors for the motor. It tries driving it. It senses how much current is being drawn. Then it knows, okay, probably it's so heavy. It has pressure sensors probably. It has probably vibration sensors, right? If the machine is unevenly loaded, right? You put a heavy blanket, then it makes a lot of noise, right? There's a sensor there which senses the vibration. So even a simple thing like a washing machine, if you don't think about it, there are at least probably 6-7 sensors easily in a washing machine. Even advanced machines have even things like sensing the water viscosity to check, whether the rinse cycles are enough and all that, right? Depending on the type of washing machine, you have different sensors. So today, every device, a lot of devices in your home have embedded controllers, and today things like Wi-Fi controlled bulbs, everything is becoming common today, right? You have smart plugs. You plug in, that plug is automatically monitoring what is being consumed. So there are so many embedded devices in a typical house. You are, probably your calling bells are also getting advanced. You have surveillance cameras in the house today. Many people I have seen, if they have an old person living at home, probably their children are living abroad or whatever, right? Many of them install, I have seen surveillance cameras in the house to check, make sure once in a while they check, where everybody is okay, old person, they don't have a fall or whatever, right? There's so many sensors available today. A typical house, I'm sure at least you can easily count 5-6 microprocessors running, in the different devices in your house actually. Audio visual equipment I just talked about, right? TVs, all the kinds of stuff that you have. Gaming consoles, some of you are probably familiar with it, right? Your PS5 or whatever. It's an example of a pretty complex embedded system, right? It has very high-end processors, supporting beautiful graphics, all the stuff, right? It has HDMI ports and so on, pretty complex devices. Telecommunication equipment, right? Starting from the simplest home router in your house. I'm sure all of you have a broadband router, right? So that's an example of an embedded system which is connecting you to the internet. It has probably a good grade processor which runs all the different protocols which are needed. And it has Wi-Fi functionality on one side. It supports probably a fiber interface or a ADSL kind of interface on the other side. So, but you have also all the way up, if you go to a core router which is running probably 100 terabits routing devices, right? They are also embedded systems, but they are much more complex. They will have a lot more controllers, a lot more processors. You take a high-end router from a company like say Cisco or Juniper or whatever, right? They're also embedded systems. They are their own. These companies have their own embedded operating systems, right? They are homegrown and built it over 20 years or so. But they have different cards, different line controllers, very very complex embedded system, and they also have very tight real-time constraints because they have to be able to service the data rate which is coming in and service the packets at the right rate, right? So telecommunication equipment, from your simplest home router to the high-end core routers which are deployed in the core internet, you have a huge class of devices which are all embedded systems actually. Then medical devices, right? Medical devices, very common. Some of you might have seen your parents or your grandparents using a small glucose meter, right? Which you put a strip in, it sensors, it has a small LCD. It's a simple embedded system which has a small microcontroller which kind of has some sensor. You'll see some small LEDs blinking when you keep that strip, right? It sends some light, the reflectance is measured, and based on that it gives an estimate of the blood glucose, right? You have a blood pressure meter. It's a little more complex because it has a motor, it pumps air, it senses something on the on the airflow. It's called oscillometric measurement. It senses how the blood pressure, it kind of detects whether your pulse is stopping or not, and it kind of slowly deflates it. It's a pretty complex embedded system if you think about it, right? It has to first pump, then it has to deflate slowly, and it has to keep sensing something on that through that the air hose itself. It senses some sounds, and then it takes a call. It gives you a blood pressure measurement which is reasonably accurate, right? So medical devices, these are very simple home devices. If you go to a scan center, you see those huge MRI machines or CT machines, right? They are extremely complex, sophisticated. Even the X-ray machines today are all controlled, with software. They're all digital X-ray machines which kind of get an image on a in the system first, then they print it on a actually the X-ray you get nowadays are mostly digital X-ray, right? Earlier it was directly on a film. You put the film and it gets exposed. But today the exposure is done, it's captured in a sensor, then you print it out on whatever size you want. So digital X-ray machines, CT scanners, even the blood measuring, you give a sample of blood, right? That gets analyzed, right? They are all embedded systems today. So you have variety of embedded systems. They all have their own sensors. And again, from the very simple to the most complex, right? If you look at a home, blood glucose meter, you don't have to worry so much about things like safety and all that. Whereas if you're talking about a CT machine, right? CT, if you're familiar, it uses X-rays, right? The X-rays themselves are harmful. So how many times can you, and a CT typically takes at least, some 40, 50 X-rays to construct a three-dimensional view of an organ or whatever. It keeps taking slices of that particular organ. So you have to really precisely give the dosage, right? That X-ray exposure is controlled by software. In fact, if you read up, there have been cases where some X-ray machine malfunctioned and exposed patients to a higher dosage than required, right? So these machines also undergo stringent testing, approvals by regulatory agencies. They test the software for all these high-end devices, which especially things like radiation and all that, right? They are tightly controlled by agencies like FDA in the US or equivalent in India. So you have to get what is called regulatory approvals, where the entire embedded system is thoroughly evaluated, tested. Both the hardware and software has to meet a lot of standards actually. Okay, so those are examples. Again, you can see the whole class again. What is important to understand is embedded systems span an entire spectrum, right? Then cars and vehicles, right? Cars and vehicles, again, you have embedded systems. You can look at the infotainment system, right? You have those small things where you see the Google Maps integration or all the audio video. That is probably not very real time, not too many real time constraints there. But then inside an automobile, you have so many devices. You typically have an anti-lock braking system, right? You press your brake on a surface which is not having enough grip. There are sensors which automatically detect that you are losing traction, right? It senses that the car is moving, but the wheel is not spinning. So, which means, there is an accelerometer which senses there is movement, but the wheel sensor is saying wheel is not spinning. So there are two sensors which inputs are used, and it releases the brake immediately, right? That's how an anti-lock braking system works. It will release and brake again. So you will see sometimes if you are braking on a rough gravel surface, you will see a judder on your brake pedal, which means the system is actually working. It brakes, releases. It makes sure you get steering control, right? If the problem is if the wheel is not moving, you cannot control the direction which the car is moving, right? The car can turn, skid, and all that. So that again is actually a system which has a lot of real-time constraints, right? You have to be able to sense and immediately take action, right? You cannot delay the action. So they are controlled with small microcontrollers, but they are really built, tested with so many things, an anti-lock braking system. Your power steering, right? Electronic power steering or electric power steering which you have today, it's all controlled by systems, right? You move the wheel. There are sensors which detect how much the wheel has moved, and they in turn power the motors which move the actual hardware mechanism which moves the tires, right? So there are enough, even an average automobile today, most of the cars that you buy have several embedded systems, your lighting control, your switches, most are soft switches. There are so many of them actually, right? And if you open up an automobile, you'll see multiple small microcontrollers embedded in multiple. Your fuel injection is controlled by, there's something called as an ECU, which controls a lot of operations about a car. Most cars today, when you press the accelerator pedal, it does it directly. Olden days, maybe 30 years back, you press the pedal, it immediately change the wall directly. Today, nothing is direct. You press the accelerator pedal. There's a lot of electronics and microcontrollers in between which senses that it knows that you're trying to. In fact, when you press the accelerator, it just indication to that ECU saying, I want to accelerate. Then it takes decision how much fuel to pump in, what is the ratio and all that. And if it's an automatic car, it decides whether gear has to be changed. So typical cars and vehicles have today huge amount of embedded microcontroller systems actually, right? Then you talk about things like motion sensors, right? You might have seen motion sensing lights, right? Even in an apartment today in the basement, they have installed all motion sensing lights to conserve power. I walk out, it senses the motion. There are some sensors, and immediately light gets turned on. Then manufacturing equipment, right? High-end manufacturing equipment, you have a lot of embedded devices actually, like from, it's showing some examples here, but many manufacturing equipment have embedded control. You talk about a CNC lathe, right? It's called a numerically controlled lathe, which kind of used to program. If you keep a raw metal and you program it, it kind of shapes the part as per the given design. So they're all embedded control systems actually. So today, this is just, I wouldn't say this is a very complete example, just a sampling of what is there today. We don't realize, but today we are surrounded by embedded systems, pretty much. We don't even think about it. It's kind of, it's there. That's why it's called embedded, right? You don't even see it. It's embedded inside, but you only see the functionality of it and you use it actually, right? There are so many more examples that you can talk about, but just to give you a feel of, but so these are, you see that difference and you understand what things are, right? Okay. Now we'll move on to different, we talked about it in the earlier discussion also, but to give a more formal definition, right? So most embedded systems we said have timing constraints, right? Okay. Now you can broadly classify them as what are called, hard real-time systems or soft real-time systems, okay? So hard real-time systems are ones where, there are to be many definitions. I like this definition, where you can say failure to meet a constraint can lead to disastrous consequences, right? It could be to men, material, or loss of equipment or whatever, right? So systems which have such a constraint, they are generally called as hard real-time systems, okay? We saw some example, I talked about, say, rocket flight control, right? If you didn't act in that precise millisecond, or there may be a window of 2-3 milliseconds to take an action, then you probably lost the rocket, and that probably means millions of rupees or whatever, right? And worse still, if the rocket goes to a wrong trajectory and crashes into a populated area, there's probably even loss of life or property or whatever, right? So that's an example. Nuclear control systems, right? Reactor control systems. In nuclear reactors, continuously a lot of parameters are monitored, right? If you send something like a meltdown, you have to immediately shut down the reactor, right? You must have seen the Fukushima earthquake in Japan, right? So they had decent systems. That's why it was not a major disaster. But despite that, they still had some spillover, some nuclear material got leaked and all that, and it's still taking time to clean up that stuff that happened there, right? But today, most systems have to be built with a lot of security, safety. Probably in a place like Japan, everywhere they will have things like earthquake sensors. If they sense something is happening, they have to shut down the reactor immediately, right? So, and it all has to happen in microseconds or milliseconds before something can happen. Avionics software, right? Most modern fighter jets and all that, they have a lot of software which control the avionics. Like they're all fly-by-wire systems, right? You move something, you move your rudder or whatever. It's not directly controlled. You move a lever here, there's a sensor which has to move the rudder, or you want to change the flaps or whatever. Everything is controlled by what is called fly-by-wire, which means they are not physically connected. You are moving some lever. If you want to tilt the plane to the left, you move a lever here to the left, but a lot of sensors actually are detecting it and moving some control surface on the wings to take that action. But that's all completely controlled by embedded software. So that's again very, very, very hard real time. If you delay that, you are not going to be flying the plane properly. I talked about anti-lock braking, X-ray machines, everything. These are all systems where the timing constraints are extremely critical for the safety of the person operating or somebody around or whatever, right? Or failure to meet the timing constraints are going to be resulting in loss of probably life or property or huge financial damage or whatever. So these are classes of systems which are called hard real-time systems. And then the other class, what we call a soft real-time, you have constraints, you have some real-time constraints, but there's a little more tolerance, right? For a good example would be, say, a home router, right? So in a home router, what do you have? You have probably a Wi-Fi interface on one side, and you have probably, if you have a fiber connection coming in from Airtel or ACT or something like that, you have another interface to take the packets from there. Now, the timing constraint here, what is the timing constraint? Say you have the fiber is say 100 Mbps, right? So what is 100 Mbps? 100 megabits per second, right? That's the rate at which packets are coming into the router, right? When the data is transmitted from the other end, from the your provider's end, incoming packets, for example, are going to come at 100 megabits per second. And typically these are probably say Ethernet over some kind of a fiber protocol or whatever. Each packet, if you calculate the timing, you may find that okay, I'm going to get probably one packet probably every say 100 milliseconds or 100 microseconds. It's typically 100, when you go to megabits per second, it's going to be in microsecond range, right? So I'm going to get a packet when transmission or reception is happening at full speed. The router is going to be getting on that fiber interface, the cable that you're plugged in there. There's a packet coming in, say every 100 microseconds, right? Now, your processor, your software there has to be able to receive packets at that speed. It has to be able to process packets at that speed, right? Which means the capacity, the memory, everything should be designed in such a way that I am able to receive one packet and safely store it and probably send it to the other side, right? What is the router doing? Packets are coming in from the net. Maybe I am browsing, so probably I am downloading a movie, right? That's when I'm going to get huge amount of data coming in. I am streaming on YouTube. The packets are coming from the other side. So this packet has to be received by the router, sent out on the Wi-Fi side, and the Wi-Fi side has to broadcast it so that I get it on my laptop or on my mobile phone. I'm able to see it, right? Now, so if, for example, for some reason, right, maybe some conditions, there is some overload in the system, I drop a packet. I'm not able to receive one packet properly, right? Generally, in these systems, it is not a catastrophe, because what happens is if there's a packet loss, right, there are different levels of protocols and controls to deal with it. One is, for example, the video player, right? I'm playing a video. One frame loss, the video player may recover. It may just extrapolate the previous frame, so you will not even probably notice that I lost a frame. The other thing is, there will be upper level protocols like TCP, AP and all that, right? There's a frame loss, there's a retransmission which happens, right? Which may cause some delays, but you still get the packet back. Maybe for a video, I can even ignore the packet. But if I'm saying downloading a file, then I cannot drop a packet, right? The file has to be properly received. In that case, the TCP retransmission will kick in. So the router will say, no, I lost a packet. So the upper layer, basically the TCP layer will detect maybe packet that frame number 23 didn't come. So it will send a message to the other end. The other end will retransmit the packet. So basically these are systems, though there are constraints, there are ways to recover from it. But if you keep not meeting the constraint, the performance will be dropping, right? Instead of being the router is probably capacity is 100 megabits per second, but if it's not well designed, you may not get the throughput, right? It may take forever to download that file. So occasional failures are still fine. They can recover because the entire software stack is designed in such a way that you can recover from such errors. But it doesn't mean there are no constraints. But if I don't receive any packet in time, right, then there's going to be continuous retransmit, the system will collapse. But I can tolerate maybe a 2% packet loss or a 3% packet loss, which is still recoverable, right? That's an example of a soft real-time constraint. Similarly, digital TV, smart televisions, right? They all deal with these things actually, right? You have to probably refresh the display in time, right? Because in a digital television, so I mean, if I'm streaming from the net, I'll have to be able to send a frame to the frame buffer so that on the screen it's looking fine. But if there's a delay, one frame loss, a user may not be able to perceive, right? 24 frames per second, if the same frame is replayed, you don't see it. So there are constraints, but there is a tolerance based on the user level, perception ability or whatever, that you don't see that. Surveillance camera. There are many devices where you can tolerate some, delays, some errors, but still the system is still, working fine. Surveillance cameras, for example, right? Maybe one frame missing may not be a problem, right? As long as I capture maybe instead of 24 frames, if I capture 20 frames also, I can still see what happened. If an intruder came, I can still spot that in a second, 20 or 24 is not going to cause a lot of issues, right? So essentially these are systems where you have constraints, but they are not something which will cause a catastrophe if you don't meet it, right? So that class of systems are called soft real-time systems. Okay, these are some examples. Digital watches, you have a wristband which keeps counting, as you walk and all, right? If it doesn't count very accurately, you're not bothered, right? Most of them do a decent job, but instead of counting 1000, it said 990 steps, which is still okay. It might have missed some inputs based on the, the sensor or the throughput or whatever, right? So there are margin of error which is built into those systems, which are still tolerable. So this is the thing that you need to be aware. So when you're designing a system, the amount of effort you'll put in software and all that also will vary based on that, right? So it depends whether you're working on a hard real-time system or a soft real-time system. The development time also will be high. If you're developing something like a rocket flight control system, even to develop that, probably 100 kilolines of code, the development time may be 1 year or 2 years, because you have to really test each and every bit out of that. Whereas if I am developing software maybe for a home router, the development life cycles are much faster. I may be more interested in delivering a new protocol within the next 6 months instead of worrying about whether it's 100% tested or not, right? So you take trade-offs based on the class of systems that you work in actually. So coming, to summarizing this session, right? So we looked at what a typical embedded system is. We understood, typically microcontroller-based embedded system, you'll have a basic CPU, input, output, sensors, communication devices, and so on. We looked at what are the attributes and what are the design parameters, the importance of, cost, performance, and reliability, and so on. We looked at all those attributes and design parameters that we need to worry about. Then we also took a look at what distinguishes an embedded system from a general purpose computer system. What are the constraints, what are the freedom you have as a designer, what are things that you have to worry about, and as a user, what you can do with an embedded system and what you can do with a general purpose system. And we also looked at real-time systems and the two broad classes of real-time systems, which are like hard real-time and soft real-time, and what distinguishes them. Okay.